welcome back. In the last video we saw an introduction to RNNs. RNNs, remember, stand for recurrent neural networks. I told you about two important properties that RNNs have that typically CNNs and ANNs can't handle. One of them was variable length, and the second thing is sequential data. Okay. So, as I had said a few times in the last video, the basic purpose of RNNs is to be able to handle variable length sequential data. In this video I will show you a short example, again borrowed from MATLAB's examples, this time explicitly borrowed from what MATLAB has given in their deep learning toolbox, and hopefully you will see what specifically we mean by variable length. Sequential data should already be intuitive to you. So, the purpose of this video is not to actually introduce you complete to RNNs, but to introduce you to what the use case is, how are we going to use it. Okay. Hopefully it will give you some intuition about what we are going to do. Now, when we were looking at RNNs, we looked at various classifications. These classifications are not really official classifications, but they are given by a very good researcher, Andre Karpathy, and what we are going to look at in this example is a many to many classification. Recall that a many to many classification, there were two subsections that we looked at. Again, this is Karpathy's way of doing it. So, suppose you have various inputs, they could go through the sequence of hidden layers, and suppose you have an output corresponding to each of these inputs. This would be a many to many classification. Okay. Now, we will do an example of that sort shortly within this video. Now, I would like to draw an analogy between what you will see here, and this is called sequence to sequence classification. So, I am going to give an analogy between this and what happened when you did something like semantic segmentation when we were looking at CNNs. In CNNs, we tried to label each pixel as belonging to body 1, body 2 or body 3, as Dr. Ganapathy showed you. So, a sequence to sequence classification is somewhat similar. Okay. What does that mean? It means that suppose you have a time sequence and a few possible events could happen. Okay. So, the few possible events, so I will give you one good example of this. So, let us say you are driving a car and you have your cell phone in there. Remember that cell phones have accelerometers. If you do not know this, it is an interesting thing. So, what a cell phone has within it is some way to figure out which way the acceleration is going, and the reason for this is a simple reason for this is so that when you rotate your cell phone, the picture can rotate too. So, if you have a smartphone, it has first brought out by iPhone, as you remember. So, this has this capability to rotate your picture because it needs to know which way you are accelerating and which way is up and which way is sideways. So, cell phones have these accelerometers. So, let us say you keep a cell phone within your car, okay, a smartphone within your car, and by your acceleration signal it should be able to say whether you are stationary, whether you are moving at a whether you are accelerating or whether you are in an accident. Now, this can be particularly useful, and I am not sure, I have heard of a person who actually did this, a student who did this from IIT Delhi as a project. I am not sure whether he used machine learning or not, but basically the idea was, suppose you have an acceleration signal for your car and you suddenly have a rapid change, you can kind of figure out that this person has been in an accident, or at least the cell phone can figure out that this person has been in an accident. So, a sequence to sequence classification for this would be at each point it will say moving, moving normally, and at this point it will say in an accident. Okay. So, in such a case and in fact what this person did as I heard it was based on the acceleration signal of the cell phone, this person was able to alert the local ambulances or the local police authorities, because apparently the strongest saving of a life can be done at early times, and by the time this person is an accident, somebody sees that this person is an accident and calls the police or the ambulance or somebody, it is already sometimes too late. But if the cell phone can figure this out and can call immediately, then this is a great case. So, I am going to show a variation of this actually given by MATLAB, also based on accelerometer data within a person's pocket. Okay. So, let us see that case. So, the example that I am going to show is from this link. This is both available within your online MATLAB account for the duration of this NPTEL course. So, I am going to just introduce this case, and I am not going to show you the training really, I am just going to show you snippets of the code from here and actually snippets of the description given by MATLAB itself. I would highly recommend that you actually go to your online MATLAB account and run this code. This is also available directly from MATLAB's website, the website that I have shown here. Please take that, run that code and see for yourself how this works. There will be a few terms that will be used throughout this video. One of these terms will be LSTM. Okay. This is a term that I have not explained so far. This is a type of RNN, okay, the most popular architecture of RNN available today. So, the relationship between RNNs and LSTMs is somewhat similar to the relationship between CNNs and any particular architecture, let us say LANET or AlexNet, all those architectures that you saw. So, LSTM is a certain type of architecture of an RNN. So, that is what is used within this example. So, whenever you hear LSTM, please think simply RNN. Okay. So, let us come to this example. So, this is from MATLAB's own description of this problem. So, as it says that it is using LSTM, which stands for long short term memory, as we will see later, and we will see the reason for this term also. Okay. So, now what we are going to do is a sequence to sequence RNN or LSTM network. Basically what it takes is, it takes each time instant and it predicts what is the activity. So, that is the basic task here. Okay. So, time instant to activity prediction. Okay. Now, this can be tremendously useful. I told you one simple way of using it with, let us say, the car keeping an accelerometer within the car or keeping a smartphone within the car. But in this case we are taking a toy example. This is a person, let us say this person has their cell phone attached to their body, and based on the activity the cell phone is supposed to figure out whether this person is sitting, standing, walking, dancing or running. Okay. So, these are the 5 classes that we are going to look for. Okay. So, that is shown here. So, the accelerometer is not measuring acceleration in only one direction, but it is actually measuring acceleration in 3 different directions. So, the sensor gives you output in 3 different directions or accelerations in 3 different directions, and you measure this data for 7 different people. This is the training data. So, as you can see, we are throwing up a lot of numbers. Let us sort of disentangle them shortly. Okay. Okay. Now, where does the variable length come in? So, each sequence has 3 features. What are these 3 features? Let us call them acceleration in direction x, acceleration in direction y and acceleration in direction z. So, these are the 3 features that the sensor is throwing up at each time, but it varies in length. Why does it vary in length? As you will see shortly in a graph, what is it that we are measuring? What we are measuring is, suppose a person, so let us say I wear this cell phone on my body or have it in my pocket. So, let us say I draw a graph with time and I am doing some activity for a certain length of time. Okay. So, my acceleration signal looks like this with time in x, looks like this in time with y, and looks like this with time in z. Okay. Now, suppose I am wearing this accelerometer for, let us say, 1 hour. Okay. So, the length of this sequence is, suppose I am taking a signal every 5 seconds or so. Okay. So, if I am taking every 5 seconds or so, I will have 3600 times 5, I will have my length of my sequence here, because I will give one data point per 5 seconds, I am going to get 18,000 is the length of the sequence for the sensors that I have won. Now, some other person, let us say you are wearing this, but you might not wear it for 1 hour, you are wearing it for 30 minutes. In that case, your sequence length will be 9,000. Somebody else wears it for something else. Okay. So, let us say that person wears it for 2 hours and that person's length is going to be 36,000. Now, unlike CNNs where we were doing simple padding, it is sensible when you get more data and you want a sequence to sequence prediction, that you would like to take each one of these sequences and still give a prediction. This is something that is not normally possible with ANNs or with CNNs. So, variable length means your data, your time length can actually be different for different people. So, let us say if you are trying to transcribe a YouTube video and you are trying to say, what has this person spoken, or you have Alexa, or you have Google, Amazon's Echo, something that is transcribing our speech. Not all of us are going to speak for equal time instants, each of us will have variable lengths. Similarly, you want to interpret or translate a sentence, each of these sentences is of different lengths. That is what is meant by variable length. Okay. So, this is an important property of an RNN, that the length of the sequence can be different for different data sets. Okay. So, each data set can have different lengths, even though the number of features is the same. Okay. So, please distinguish between the two. When we say variable length, we mean the length of the time sequence over which this data is given. That can be different for different samples, that is the advantage for RNNs. Okay. And your final test data might be of an entirely different sequence length. So, suppose I could say I could just give 30 seconds of data and say what was this person doing. Okay. It would be a very short sequence thing, but you could still be able to classify. Okay. So, number of features however is always fixed, that is the case whether you have ANN, whether you have CNN or whether you have RNN, number of features we will fix. Okay. So, this is the problem that we are starting with. We are given AX with respect to t, AZ with respect to t, AY with respect to t, and we want to predict at each time instant what was this person doing. Such a task is called a sequence to sequence classification task. Okay. So, the way MATLAB does it is it has its own data set, and I recommend that you see this data set from the website yourself and maybe explore it a little bit. So, it has a human activity training data set. Remember, this has 7 people, 3 features AX, AY, AZ and variable length. An important property of the RNN which I mentioned even in the last video is when we take different data points, the structure of the RNN is such that these have to be equally spaced in time. Okay, for engineering problems this I would recommend very strongly. Okay, for engineering problems it is best when you are genuinely dealing with time, as against let us say a language task where one word following the other is not really a time problem, but when you have an actual engineering problem where time is one of the variables with respect to which you are doing an RNN, please try and use RNNs which are equally spaced in time, or get data sets which are equally spaced in time. This is an important notion that you should be aware of. Okay. So, here we will assume that the sensor took its data at equal time instants. Okay. If you do not do this, it will be much harder to train it because of certain features of the RNN which I will point out. Okay. So, let us say we load this and we print what this X train is. So, you can see that this training set has 6 people. I had said 7 people, but we are basically keeping 1 for testing. It is a small data set you can't really do that 60-20-20 split, etc. So, you take 6 people and trying to predict for 1. Okay. So, this training set is simply 6 people. Now, notice each of them has 3 features. So, this is example 1, example 2, example 3 up till example 6, okay. But each of them has different sequence length. So, person 1 actually measured or their activity or continued their activity for a much longer time, because it is going for 64,480, whereas this person is probably the shortest in this data set. This person went for 50,688. Okay. So, this is to say that you can train even though each person actually gave you data for different lengths of time. Okay. So, that is the advantage of an RNN. Okay. Let us now visualize the data. So, we will just take person 1 and take one of the accelerometers or one of the directions or one of the sensors in the accelerometer and plot just that. Okay. So, that is what is plotted here. You can see the time step 10 to the power 4 up to approximately 6.4 into 10 to the power 4. So, 64,000 data sets, data points, and we have the time signal. What we have plotted here is the signal of the accelerometer. Now, as should be fairly obvious, when the person is sitting, you do not see very much acceleration. Maybe this person, like I am moving around, moved around a little bit. Okay. Now, this data set is labeled. What we have labeled with is, we know the activity this person is doing. This person is sitting, and at this point, at each point you say that the person was sitting. I will show you how to represent this in an RNN structure shortly. Okay. From this point to this point, the person got up, and you can see there is a rapid change in acceleration, but as of now we have still labeled it. The label we gave was that of simply sitting. We will see the effect this has on the test set much later in a later video. Now, at this point this person is simply standing, that is the label here, and you can see that even here the variation is not much, but also understand that somehow this thing is supposed to figure out how well this is doing based on here or here. Okay. Now, when the person is walking, you can see a lot of variation in the person's acceleration. Okay. So, this portion is walking, then the person starts running, and finally the person is dancing. Okay. So, this is the data set that is given to you, but just based on acceleration in one direction you can't figure it out. You have to see acceleration in all 3 directions. When you are dancing, maybe you will jump around a whole lot more and your acceleration in Z will be more. Similarly in running also. Okay. In walking it will be less intense in some direction or the other. So, it is a combination of these 3 activities with which the accelerometer is supposed to, or with which your RNN is supposed to figure out whether this person is dancing, walking, running, etc. Overall, the important thing here is to see that there are 5 classes, 3 features. Okay. Of course, we know that 3 features corresponds to the input, 5 classes corresponds to the output. Let us now use this to create a RNN architecture, or within RNNs we are basically creating a LSTM architecture. So, we will create that, and I will explain how this gels with what I showed you in the last video, and hopefully things will be much clearer at that point. Okay. So, as I said just before, our input sequence has 3 features and it has 5 classes as output. Okay. So, suppose I draw that in a figure, just a single point. If I write x, what comes out is y or y hat. This is supposed to have size 5, this was supposed to have size 3. Okay. Now, why did I write 3 cross 1 and not 3 cross 64,000 or something? Because this is only the first time instant. Okay. Okay, remember this is a sequence to sequence classification task. I take the first time instant and somehow I am supposed to predict what y1 hat is. Okay. Now, the magic thing there is this layer in the middle. This is what we typically call H for hidden layer, which is the terminology that we have used within neural networks right from the beginning. Now, what is the size or what is the number of neurons in the hidden layer? I will call this H1. What is the number of hidden neurons in the hidden layer? This is once again like we were doing before, it is our choice. Okay. Only thing is, once we choose it, through the time sequence we will keep this fixed. Okay. So, this is in this case the MATLAB example has chosen 100 units, but you can choose any number. Obviously, if you use smaller you will have lesser expressibility, but you will train faster. Okay. So, we are going to choose 100 units for this particular example. So, effectively you can see this as 3 input neurons here, hundred hidden neurons and 5 output neurons. This is the neural network except turned on its head like this. Okay. So, we usually have neural network going this way, we have neural network going this way. Okay. Now, what is an RNN? An RNN is multiple such neural networks put together. Okay. So, I start with x1, have h1, get y1 hat. Okay. But this h1 is not wasted, it goes to another h2 which also takes an input from x2. Okay. So, please notice what is happening here and see what in some sense makes RNNs work. What is it? Whatever output or whatever hidden layer, whatever features this hidden layer had, those are not wasted, they are reused into the second time instant. Okay. Because you want to know what happened before, you do not want to forget that. We are not taking y1 hat, remember all we are taking is the hidden layer input. Okay. This is sort of like what Dr. Ganapathy talked about in transfer learning. I have already learnt something, why waste that? I will transfer that information here. So, this input goes here, h1 goes here and h2 is predicted, y2 hat is predicted. This is like recursion. Not only do I want to know what happened now, I want to know what happened a little bit before. Then I take x3, y3 hat, and the prediction method goes on like this. We will see later how to find out the losses and back propagation for such an architecture, but you can go till some final time. The point of an RNN is t is variable. Okay. When we say variable sequence, that is what we mean. So, x1 is 3 cross 1, x2 is 3 cross 1. What does x1 correspond to? x1 corresponds to the 3 accelerometer signals at time 1, x2 corresponds to 3 accelerometers readings at time 2, so on and so forth, up until time n or time t you collect the 3 accelerometer outputs. Okay. So, what we had shown here was 1 accelerometer. Similarly, you will have 3 such things at each time instant, that is what you give here. Okay. Now, what is y1 hat, y2 hat, y3 hat? You know this before, this is simply for a classification task. This is simply the softmax output. Okay. Another way to say it is our approximation of a 1 hot vector. We know that this has to be either 0 1 0 0 0 or 1 0 0 0 0 etc., and we will approximate it through a softmax output. Now, MATLAB in this particular example has chosen slightly differently. I will show you that. Before I show you a little bit about terminology, oftentimes in later videos I will say number of layers. That is strictly speaking not correct. Number of layers should be in this direction. This is length time or sequence. Okay. But I will sort of abuse notations and I will say, you know, when the number of layers increases, it is going to be very difficult to train, but you should understand that number of layers actually is in this direction. Right now I have shown you a case with effectively one hidden layer, but just like we had neural networks before this which had more than one layer, you can simply do the same thing. You can take x, put let us say 2 layers and then get out y. In fact, MATLAB has done something similar. If you see their description, after the hidden layer there is a fully connected layer, okay, which you know what it means. So, after this, so let us say I start with x1, I have a hidden layer with 100 neurons. After that I can put a fully connected layer of 5 neurons, which means, you know, you are going to get a fully connected thing here, and after this you have softmax, okay, with 5. Okay. So, you can make a softmax layer after that, usually use our softmax prediction formula and then go on from there. Okay. But similarly you can put 8 layers, 9 layers, typically people, you know, do not go more than 8 layers, and these are for very complex tasks. I will show you a small example in a later video of a language task. Okay. But typically in layers we go somewhere between, for engineering tasks usually 1 or maximum 2 are good. Okay. So, especially if you are dealing directly with numbers, 1 or 2 layers is usually good enough, and you will see that it actually takes a lot of effort to train such things. Okay. Now, what is special about this RNN is, remember that the weight that goes from length to length or time to time is exactly the same. Okay. Recollect, if you have xt, ht minus 1, ht coming out, and let us say y hat t, then ht is, let us say I will say tan h in this, but some non-linearity of some weight matrix multiplying xt plus some other weight matrix multiplying ht minus 1. The subscripts are as follows: for xt I will call it wxh, for ht I will call whh, and of course you have to add a bias term. Okay. Now, for this example let us see what the sizes of these matrices ought to be. Okay. So, let us see this. Xt at any point is a 3 cross 1 matrix, H is a 100 cross 1 matrix. So, what should be the size of wxh? Please think about it. Similarly, ht minus 1 is a 100 cross 1 matrix, ht is also a 100 cross 1 matrix. What should be the size of whh? Please think about it. ht is a size of 100 cross 1, what should be b? Okay. If you are thinking about it, please pause the video for a second, think about it, work it out and then come back. I will show you the answer after you return. Okay. I hope you tried it. So, as you can see, wxh takes in a 3 cross 1 matrix. Okay. So, this is 3 cross 1. This should give you a 100 cross 1 matrix as output, which means wxh has to be 100 cross 3. Similarly, whh has to be 100 cross 100, so that you can take a 100 cross 1 matrix and give a 100 cross 1 matrix as output. Simple dimensional consistency or length consistency requires that you have 100 biases for a 100 cross 1 matrix here. Okay. Now, giving all this is fine. how many parameters do we have? You have 300 parameters here, 10,000 parameters here, and another 100 parameters here. Okay. So, you have 300 plus 10,000 plus 100. So, which is 10,400 parameters for this problem. Now, you may question that you have 10,400 parameters, but then what happens at the next time step? Okay. The catch here, and which is why I said that in engineering examples it is a good idea to take the same delta t between this and this, this and this, is that we will assume that it is the same WXH and WHH and B for each time. Okay. So, the only W's you use are the W's that you will use for the first layer, they remain a constant as you go across an RNN, and that is the power of an RNN, otherwise the number of parameters would explode. So, from time to time to time to time you are going to assume that the matrices do not change, that is the relationship between H3 and H2 is the same as the relationship between H4 and H3 is the same as the relationship between H5 and H4. This basically is what gives power to the RNN. More than power, this is what gives compactness. Okay. So, once you use this, you have your RNN, you have just set your structure this way. There are various ways of compactly representing RNNs. We are not going to deal with that in this course, this is just to give you an introduction. I would recommend very strongly that even before you see the final video, you run this particular case here and see if you are able to understand what is going on. You can in fact see here that there is an LSTM layer which is made up of a fully connected layer and a Softmax layer, and finally the classification layer which will tell you how it goes. Hopefully you also saw the number of parameters that pop up in this problem, in this case 10,400 parameters, and you have to train all these 10,400 parameters via backprop. Okay. Now, how do you do backprop for this case? How do you calculate loss in such a case? This we will see in the next few videos. Thank you.